Hello and welcome back to California Geology. I'm Dr. Robert Lopez, and today I want to finish off geologic time. I'll be talking about radioactivity and absolute time. So remember, absolute time is based on the atomic clock, and that's radioactivity. And it was discovered in 1896 by Henri Becquerel. But nonetheless, what's happening during radioactivity is there's this spontaneous decay of an atom, and it results in a change in the atomic number, which means you're going to make a different atom. So you're going from some parent atom to a daughter atom, parent to daughter atoms. Now, the radiogenic atom is the one that's the daughter product, right? So this forms from the decay of a radioactive parent atom. So that's important to note that the genesis of that particular atom comes from radioactivity. Now, if you remember from our minerals talk, an atomic number is basically, it defines the atom. It tells you what the atom is, and it's a number of protons in the nucleus. Whereas a mass number is the addition of protons and neutrons in the nucleus. So by convention, we draw the atomic number as a subscript before the chemical symbol, and then the superscript would be the atomic mass, right? So there's atomic number and the mass number. And so here I have carbon 12, carbon 13, and carbon 14. All of these are carbon atoms, but they vary in their number of neutrons. And so we call these isotopes, atoms of same element but different mass numbers. In other words, they have different neutrons in their nucleus. Some of these are radioactive, and they're going to decay. They have a certain decay rate that can follow, and usually we can express it in this form of half-life. So the half-life is the time needed for the number of radioactive parent atoms to be reduced by 1/2. And so one way you can do it is to show it on a graph. And what you'll find is on this graph I have on this y-axis the fraction or the percent parent remaining. So we're going to start off with 100% or 1.0, a whole amount. And then we're going to start decaying it. And over here that we have half-lives. So every half-life we're going to decay it by 1/2. So after one half-life, we're going to be at either 0.5 or 50%. At two half-lives, we'll be at 0.25 or 25%. After three half-lives, we're going to be at 12.5% or 0.125. And then at four half-lives, we'll be here. And so what's going to happen, we're going to be cutting this in half and in half and in half until we approach this bottom curve. So what happens, it's going to develop a curve that's going to begin to approach the bottom here, but never quite reaches it because it's always being cut in half and in half and in half and in half. And so we call this type of curve an exponential curve, right? This is an exponential curve. And really what it is an exponential decay because we're seeing this decay of the atom. And there's some complicated formulas that we can work into and I'd have to kind of review them for you, but I'm going to show you a more simple way to get ages from radioactivity, and we'll use this half-life method. Now, if we look over here, the half-life equation, simple way, and the age of the sample will be equal to something called T1/2. And T1/2 is basically the time required, the half-life, for a given number of parent atoms to be decayed by 1/2, to be reduced by 1/2. And then you want to multiply that by the number of half-lives elapsed. So it's going to be the half-life of the sample, how long it takes for each half-life to occur, times the number of half-lives that have occurred. And so atoms, parent-daughter pairs, isotopes that are used for absolute dating. And really, I think your book says the workhorse is potassium-argon 1. So this would be the parent, these would be the daughters, and these are going to be their half-life. So in other words, if you had 1,000 potassium-40 atoms, for them to decay down to 500, it would take 1.3 billion years, or 1,300 million years. So note that uranium-238 decays to lead-206, and the half-life for this sample is about 4,500 million years, almost the age of Earth, 4.5 billion. Then for uranium-235 to lead-206, the half-life is 704, right? And so, and there's also carbon. I'll let you read about carbon in your book because your book does a good explanation of it. But the half-life of carbon is 5730 years. One thing I want to point out is carbon is only used for something that was once alive, a plant, an animal, but you can't use it for anything older than 50,000 years because it just doesn't go that old. Note it has a very, very young half-life. So these up here are going to be used for old rocks, for dating rocks, anywhere from 10 million years old to as old as the age of Earth, 4.55 billion years. We'll come back to this graph up here in a little bit. I'll be using it. Now, let's look at some examples. I call these exercises. And so the exercise I want to look at here is we're going to extract minerals from rocks, and then I did this in graduate school. We would dissolve the rocks in hydrofluoric acid, and then we put the solutions through these resins that would attach to different atoms and let other atoms go through. But it's basically called a chromatography, and where you can separate the different atomic elements. And so what we'll do over here in the first step, and so over here I have some examples. Here I have a sample of parent, daughter, and the half-life for that particular system. So in one sample, we measured 8,252 atoms of parent uranium, and the daughter was 1452. And then these are some other examples. So let's look at this first one first. Now, the first step here is we want to determine the initial amount of parent, because remember, the daughter is said to be radiogenic. So initially, all this came from a decay of a parent. So this used to be a 238 in this instance decay. So we're going to add those two up. So for that one, if we add 8252 plus the 1452, we're going to get an initial amount of 9704. 9704 atoms. So that's going to be the initial amount of atoms for this particular system. Now, now I want to determine the fraction of the parent left, or parent remaining. And so basically we take what we have today, which is 8252, and we're going to divide it by the total, the initial total, which is 9704. 9704. When we do that, we get 0.85, or 85%. So in other words, 85% of the sample of the parent atom is still remaining. Now we need to use the decay curve up here to determine the half-lives elapsed. So actually I have one here that's already nicely made up, and so we'll go here to 85%, which is right in here, and then it goes to right here, and then we'll drop that straight down, and we'll get a value, an estimate right in there. So each of these is 0.2, 0.24681. So this is about a 0.2, maybe a 0.25. So you kind of got to estimate it here. So a 0.25. So it's telling us that there's been 0.2 half-lives elapsed. So let's go back to our problem over here. And so now we're going to use the half-life equation. So the age of the sample is going to be the T1 half for this particular sample. Remember, it was 4,500 million years, so that's always going to be given. So we'll put 4,500 million years, and we're going to multiply it by what we just calculated from the graph, which was 0.25 half-lives, right? And so when we do this, we'll get our calculator over here, and we'll do the 4,500 times 0.25, and we get 1125. So the age of this rock or mineral is 1125 million years old. That's how we get the age of that sample. All right, so maybe we'll try one more. Now for this next one, let's go back here. Note that we'll do the potassium argon one here. And so that's the parent potassium, the daughter is argon. So the first thing we're going to do, step one for this, is we're gonna get the parent initial, right? So we got to add 16 to 11 plus 2191 to give us that total. So when we do that, we'll take 211 plus the 2191. That, but we'll add 1. So it's going to be 18402. 18402. So that's going to be our parent initial. Now, the next step we want to do here is determine the fraction of the parent left, right? And so we just take what we have today divided by that initial. So here we're going to take that 16. So x here is going to be 16 to 11 divided by this 18402. And when we get that, let's try this one. So it's going to be 16 to 11 divided by 18402. So here we have 88% remaining. So it's going to be or 0.88, 88% of the sample remaining of the parent. So now on our decay curve, we'll go to 88% there. So let's go to 88%. And so 80, it's almost 90 up here. We'll go across here. And in fact, it's going to land right in here. And we're going to be a little bit than 0.2. So remember, that's 0, 0.2, 0.4. So let's say we're at a 0.17. So this could be like a 0.17. That would be how much we have left for this sample. So now doing that, we've determined our number of half-lives, which is 0.17 for the sample. Now we use this age equation, right? So it's going to be that the age equals the T1/2 for this sample, which is 1300 million years. So that's given, right? I'll always give you that. It's up here in the table, 1300. And then times the half-lives elapsed, which are 0.17. 0.17. So when we do the math here, we're going to take the 1300 times 0.17. And so that gives us 221. So the age of the sample is 221 million years. So that's how we do this work here. And I mean, you can do it you can make up your own numbers, but we really measure them from crystals, from minerals. And so if you'd like, you can actually do this one on your own here. The uranium 207 to lead 207. So you'll want to add these two up, figure out the percent parent remaining, with this equation here. Then go to the decay curve, and you could actually use one that like this one here. You could just make your own, like I made this one here. If you use graph paper, you might be able to get it more fine-tuned. Figure out where it's going to intersect, and then drop down to get your half-lives elapsed here. And then you want to use the age equation to determine the age of the sample. So try that. I'll give you a couple of more examples. Certainly I have one of these on the next exam. All right, well, we'll stop.